Well, Wilson, here we are. Stuck here forever. Do you want to hear another story? Wilson, let me take you back to a time when I was studying econometrics, and in particular the ordinary least squares estimator. First, I will have to explain regression analysis. Regression analysis is the relationship between a given variable and one or more other variables. Regression is more powerful than correlation. The dependent variable, y, is assumed to be stochastic, whilst the independent variable, x, is non-stochastic. A practical thing to do to see if there is association between two variables would be to draw a scatter graph. Here, Wilson, we can say x and y are correlated. But this tells us nothing of the predictive relationship between them. We can use the general equation of a straight line to obtain a line of best fit. However, Wilson, this relationship is completely deterministic, and clearly not realistic. Therefore a random disturbance term, u, is added. Subscript t denotes the observation number. Wilson, you are probably wondering how to determine the values of alpha and beta. We choose values for alpha and beta so that the distances from the data points to the line of best fit are minimized. A popular method is the ordinary least squares. Note, Wilson, that the vertical distances are usually minimized rather than the horizontal distances to the line. This is under the assumption that x is fixed in repeated samples. The problem then becomes one of determining the appropriate model for y, given the observed values of x. With the OLS, you take the vertical distance from each point to the line, square it, and then minimizing the total sum of the areas of squares. Let yt denote the actual point for observation t, and y hat denote the fitted value from the regression line. The difference between these is u hat t, also known as the residual. Taking squared distances ensures that all deviations that are calculated are positive. The term given to minimizing the sum of squared distances is the residual sum of squares. Don't forget, Wilson, that u hat t is the equivalent to the difference between the actual point and the line. Let L denote the RSS. This is known as a loss function. We also let alpha hat and beta hat denote the values of alpha and beta. By minimizing the RSS, the loss function is minimized with respect to alpha hat and beta hat. Essentially, L is differentiated with respect to alpha hat and beta hat. The above equations are the coefficient estimators for the slope and intercept of the best fit line. They imply that the line goes through the mean of x and y. This alternative equation for beta hat is equivalent to the sample covariance of x, y, divided by the variance of x. What did you say, Wilson? You want to know why we use the OLS and why it is so desirable? There are 4 assumptions underlying the classic linear regression model. If these 4 assumptions hold, then the estimators of the OLS, alpha hat, and beta hat, will have some nice properties and are known as best linear unbiased estimators, or BLUE. I miss my wife. Anywho, the 3 desirable properties are consistency, unbiasedness, and efficiency. These 3 properties are why the OLS is so highly regarded, Wilson. Say, Wilson, I think all this OLS talk is making me crazy. Wilson? Wilson. Come back. Wilson. I am sorry, Wilson. I love you, Wilson.